Okay, on the bench this morning we have a new addition to our test equipment, and what this is called, and I've already featured just kind of hooked up like this on the frequency counter video that I did, is a device that we call, let me see if I can turn this around. Well, let's shut this off here for a minute. Okay, a Rubidium frequency standard. Now, what the heck is this and why does it matter? Well, basically what this thing does is you find these a lot in very accurate RF equipment, such as like a cell phone tower, for instance, okay, where you need a very accurate frequency standard from which all the other frequencies will be generated. So like in a cellular tower, you do not want the frequency of your cellular station to drift or to be inaccurate, because that could greatly affect the function of the cell tower. So what these use is a hold on. Okay, everybody, we're going to cheat here. I am on everybody's favorite information place, Wikipedia, and although they're not always perfect, sometimes they do get the basic information across, and in this case it does. So basically, what is a Rubidium standard? It's basically, I would consider it a low-end atomic clock. Okay, we've all heard the term atomic clock before. An atomic clock is, is what we use to regulate our time in the world, right? Because of their accuracy. So, as you can see, a Rubidium standard or Rubidium atomic clock is a frequency standard, okay, in which specified hyperfine transition of electrons in rubidium-87 atoms is used to control the output frequency. So basically, the radioactivity of an element is very accurate. So when you hear about, when we talk about that a radioactive element has a half-life, okay, you've heard the word half-life before, and that is the period of time that it takes a radioactive element to have 1/2 of the radioactivity as it did from when you started counting, okay? So basically, that radioactive decay is very, very, very accurate, okay, based on the element. So in this case, we're using rubidium, and we're using the atomic activity, and basically, without getting too crazy with science and all that, basically we're using that radioactivity as a standard clock, okay? Now we can build circuitry to use multiples of that, or to fine-tune that into a certain period of, frequency, which is, cycles per second. Most of these atomic clocks will have usually anywhere from 5 to 25 megahertz is typically where you'll see them at. This one that we have here, and you can see it, has been modified. It's been specifically modified by the place that I purchased it from, so that it has an output of exactly 10 megahertz. And if we look up at our oscilloscope here, let me zoom you in, you can see that it's 10 megahertz, okay? Now, of course, the frequency counter on this is it jumps around, but the bottom line is you can see it's 10 megahertz, okay? And, of course, as this thing reaches its ambient operating temperature, it gets more and more stable. So really one of these needs to be on for a while for it to settle. And if I connected it, one of these lines here is just an active low signal that you can connect to an LED, and that's called your lock signal. And basically, once the oscillator has reached its ambient temperature and has locked in on its pre-configured frequency, it'll pull that line low as an indicator that it's locked. So then what you do is normally you'd put a little LED there, and when the LED comes on, you know that this thing is warmed up and locked in on its preset frequency. In this case would be 10 megahertz. And you can actually see when you first turn these on, they're not exactly perfectly 10 megahertz. They'll kind of flutter around a wee little bit. If you have an accurate enough frequency counter, you can see this. But the longer this thing remains on, eventually it'll get to a point where it becomes very stable. And why would you want that? Why would you want a signal generator that only puts out one frequency? Well, I'll show you why here. Let's see if I can take you somewhere here where we can demonstrate. So I've taken my Rigel DG4162 waveform generator. It's basically a fancy signal generator. I've taken it down off of the shelf here to show you something on it. Now you're all familiar with this because I use it in a lot of my videos. I use it a lot for audio frequencies, but this will actually go up to 160 megahertz. So it actually can generate signals up into the RF range. Now there's reasons I don't use it for RF. Mainly because you can't get the output signal low enough, without using like attenuators and things like that. But technically it is an RF signal generator as well. You can do FM modulation, you can do sweep, you can do AM modulation, all kinds of things. But if we turn this around, this is the reason I brought this down off the shelf. And get you some light. So let me see if I can get some good light here. So let's take a look right up here. What does that say? 10 megahertz in and out, right? So this uses a 10 megahertz frequency standard as its main clock to generate all the other frequencies that you select. All right, and you can output that 10 megahertz, and it can be a reference to have all of your other devices connected to the circuit tracking with it, so that they're all synchronized to that same frequency. Okay. So this can be a 10 megahertz reference. Although it's not highly accurate like a rubidium, it will work. Okay? But if you notice, it also said 10 megahertz in. Okay? That is where this rubidium standard comes into play. Once this thing locks in, it's super accurate. If I were to run this cord into that in there, it is going to enhance the accuracy of this device. What's more, if you look at, for instance, the spectrum analyzer that I have, it has a 10 megahertz input. A lot of these RF generators and oscilloscopes and so forth, if you go to the rear of the scope and the rear of the test equipment, they have a 10 megahertz reference input. If I were to split that 10 megahertz reference off and feed it into all of these devices, okay, all of them would sync to this one very accurate reference. Not only would it make those devices very accurate, but it would also synchronize them to one another, so my test results would be very, very accurate. Okay, that's the point of this. Now, in the normal world, if you're working on a, an FM tuner or an AM radio or something, that type of accuracy is not necessary. Okay, you really don't. It's really not necessary. Okay. However, when you start dealing with very high frequency, or when you start dealing with digital, where where you're, like computers and so forth, very high frequency signals, and you're tracking them, accuracy becomes more and more critical. Working with cellular, working with Wi-Fi, a tiny little bit of error can throw you off a whole lot down the road. When you're taking this 10 megahertz and you're multiplying it, 1,000 times, all of a sudden the tiniest bit of error is amplified 1,000 times. So your simple little quartz crystal oscillator that can be off, 10 or 20 parts per million, or even 100 parts per million or higher, all of a sudden that little insignificant error becomes a 1,000 times amplified error. So that's kind of the purpose of these. So really what we're going to do today is, you can see it works. I just have a power supply clipped into it right now, but this heat sink is not adequate for this. These get very warm, and the longer they're on, the hotter they get. And you really want to keep these in an operating temperature of around 50 degrees C, no more. And you do want them to be warm, because the heat is where they get accurate, but you don't want them to overheat, because it actually will shorten the life of the device. If these are kept at a good temperature, they will last a very long time. And so I want to get this mounted to a proper heat sink. I would like to put a connector on this, where I can chassis mount it inside a case. I would like to connect the a power input connector, and I would like to be able to get a lock LED on the front of the case as well. So that's what we're going to do, and we're going to do some tests and see how it works. And I'm not sure on the power supply yet. Possibly I might just build a simple linear power supply with regulation, and just see where we go with that. And if that all sounds good to you, then stick around and we'll do it. Okay, so here's what I've come up with on this. I had this case, and it was kind of designed for like an amplifier kit. It's just like a DIY amplifier case, but kind of was awkward. Nothing fit in it right, and it just sat around for a long time, so I thought this would be a good purpose for it. So I have a piece of thick, quarter-inch thick aluminum stock that I used heatsink compound, and I mounted this rubidium oscillator to that. I made up the cables here, and you can see how thick this metal is. It's like, I don't know, it's very thick, like more than a centimeter thick, I'd say. So of course nothing fits chassis mount through it, so I had to use one of these flange mount connectors. And you can see I kind of drilled through here down in the shop and mounted it. I put an on-off switch, and this is the lock LED with the appropriate dropping resistor, and they're all wired into this connector here, the DB9 connector. And if you notice, I have this little buck converter. It's a little DC to DC converter, and basically what it does is this thing runs on 15 volts DC. And what this is doing here is it takes the 15 and steps it down to the voltage that my little fan will run on, which this is a 12 volt fan, and I have it dialed down to about 11 volts, so it's a little bit quieter and a little bit easier on the fan. Now, why does this look like overkill? Well, it's really not, because these modules, you can buy 10 of these, a pack of 10 of these little buck modules for literally dollars. It's not real expensive. And this is just cheaper and easier than trying to put together a LM317 or something like that. And it's very accurate and very easy to adjust by just turning this pot to adjust the voltage. So it works perfectly. On the back, I put some air holes. Didn't do the greatest job, but it works. You can see. And I put an input jack for the power. Now, how to power this, what I ended up using was a laptop, generic replacement laptop power supply. You can get these anywhere from old computers and things, but you have to watch. This one, if you notice, is made to put out 15 volts at 5 amps. You need a minimum of a 3 amp power supply, preferably a 5 amp. And you have to watch, many laptops use 19 volts. You put one of those in here, you're going to damage it. So very important, make sure if you're going to use an old laptop supply or something that you get 15 volts. These can be purchased online, eBay type, Amazon type places, very, very inexpensively. And since they're designed for computers, they are relatively quiet power supplies, and this keeps the power supply away from everything here for noise, so it works pretty well. So I just had to change the plug. It had a little bit bigger barrel on it, so I put a plug that fits this, and when we plug this all in, what should happen is it should come up, and then after it locks onto its 10 megahertz, I'm going to turn the scope on here, it should light up to tell us that it's locked. So let's plug this in, and let's turn it on, and you can see it locks right away, and there you go. Now, if we look at our output here, you can hear it's pretty quiet. And if you look over here, we have a nice 10 megahertz signal. And again, this frequency counter in this, in the scope kind of bounces around, but you can see how accurate it is. And that's really all there is to it. So, last but not least, I'm going to put the bottom cover on. This is the bottom. And I'll put some labels on there with my label maker, and I'll get it mounted up on the bench, and it'll be in addition to the family here. So that takes care of that, and then my next video, I finally have everything in to finish up the video on the frequency counter that we just built. So I'll be showing you that next. And if you want to build one of these, that's really all there is to it. You just need, the only thing you have to watch when you order these, there are several different models out there. This is the less common one. The more common ones out there are a little bit bigger. They almost look like a hard drive out of a computer, size-wise. They all do the same thing, but you have to be sure that whichever one you buy actually has a 10 megahertz output, because all the test equipment uses a 10 megahertz reference signal. And you got to watch, because some of these put out 15 megahertz or different frequencies. So if you buy one of these online, it's obviously going to come out, new. It's going to come out. It's going to be used. It'll come out of an old cellular tower or something like that. And you have to just make sure that the one that you're buying, because these are going to cost you about $150 or so to buy a good one that's tested. This one here, the reason I purchased it is the individual who is selling these has the means to accurately calibrate them. He adjusts them to be exactly 10 megahertz, within a reasonable standard. He also rewires them to run off of a single 15 volt power supply. They come standard wired for split power supply, where you need a 15 volt and a 5 volt. Even though this thing has an internal 5 volt regulator, it's not used in the application that these come out of. So he makes all those changes, tests it, calibrates it, packets it together with a connector, and with the 2 connectors and a little calibration chart that comes with it. So, and it's about the same price as the ones you buy from other sources that don't have any of that done. So when I get this put together, I'll go up to the monitor here and I'll try to show you the site on eBay. He doesn't always have them, but they come up every so often on eBay and you can purchase them from him. I think he makes them in small quantities, but fantastic product, and I'm really glad to have it. So that's it, and let me get this put together and then I'll show you the website and I'll show you what it looks like finished, and that'll be that. Okay, there she is in her new home, right next to our new frequency counter, and I think we're good. So next will be I got the cable, as you can see, and I'm going to load the software up, and our next video is going to be the completion of this. If you like this, give us a thumbs up, and oh, I'm sorry, I also promised that I would show you the source for these little frequency standards, so stand by and I'll get you that. Alright, I'm a little bit at an angle here for my monitor, but you can see the seller that you can get these from is RDR Electronics, RDR-Electronics, and there are other people that sell these online, but this company seems to do a really good job. As you can see, it comes with a little heat sink right out of the box. It's not good for for long-term use like that, but it works. Comes with these 2 connectors, and most importantly, it's calibrated and adjusted for 10 megahertz. So if you read in the description, you can see output has been changed from 15 megahertz to 10 megahertz. Okay, unit's been modified for 15 volts only. Okay, the unit has provisions for the circuit board for 5-volt regulator, but was not included in the cost-sensitive telecom. The regulator have been added, so you can see he's modified it to run on only 15 volts, which is really convenient. It has a serial interface that you can change some of the settings and so forth on it. They've disabled the temperature compensation, which kind of actually, for what we're using it for, makes it better. And it's been calibrated, and you can see it's less than plus or minus 2 times 10 to the negative 11th. So it is very accurately calibrated. And it comes with a calibration sheet. Each one he does a little printout and includes it with it when you buy this. So it gives you a nice little print. It gives you a little nice detail of, copy of the user manual you can get to it and download. Has all the pins of the 9-pin connector. Very, very nice. So if you're interested in that, you can purchase that. As you can see, there are also other ones that look like this. They're a little bit less money. They look more like a hard drive out of a computer shape, but they're not. They're just pulled out of a machine, tested and sold, and I don't think they do quite the job of calibrating and modifying and all that. But you can buy these. There's lots and lots of them available. They're always, the price range is going to be around that $150 to $175 range. And you probably don't need one, but if you're going to check the accuracy of your own test equipment, or you want to have a reference standard for all of your equipment to track to, this is a good solution. You can buy reference signals, reference generators commercially. Some of the big test equipment companies make them, and you're going to find out they're very, very expensive compared to these. They may be a little bit more accurate, but depending on what you're doing, the cost just is prohibitive for people who are hobbyists especially, or even people who do some repair work but really don't get into mission critical things. So again, I hope you enjoyed this video. I hope you learned a few things. If not, it was a nice time waster anyhow. There's usually nothing good on TV these days. But if you liked it, give us a thumbs up, and keep looking. We got lots more videos coming. I have a few pretty interesting ones coming up in the future here, but they're going to be a little bit slower coming lately because work has been just so crazy busy. So as I get some free times on the weekends and things, I'll do a video here and there. Anyways, have a wonderful day. Thank you all for watching. Thank you for your wonderful, kind comments. I can't thank you enough for it. I'm flattered, and I really hope that I can continue to help you guys just have a hobby, if nothing else. All right, thank you, and more to come.